Now let's consider inequalities using the word or. Here we have an example, x is less than -1 or x is greater than 3. The key word here is or. We cannot be less than -1 and greater than +3 at the same time. So when we're talking about these types of compound inequalities, x only needs to satisfy one of the requirements. X is less than -1 or x is greater than 3. An additional piece of information. In our language, there are two types of ors. We have what's called the inclusive or, and we have an exclusive or. Let's use food for an example. Let's say you're trying to decide what to make for dinner, and you have a choice of making chicken or fish. Generally speaking, we would pick one or the other, but not both. Sometimes you might have an example where you would want both chicken and fish, but most of the times it's one or the other. That is an example of what we call the exclusive or. Exclusive or means we have one or the other, but not both. Or let's say for dessert, you have a choice of cake or brownies, but mom's not going to let you have both. You get one or the other. Here's another example of exclusive or. To contrast, the inclusive or means we could have one or the other or both. Let's say we're no longer a kid and mom doesn't get to control our desserts. We could have cake and brownies for dessert. Might not be a wise or a healthy choice, but that's an inclusive or. One or the other or both. We could talk about clothing. An inclusive or could be something like we could wear a t-shirt or a sweater or both. That would be an example of an inclusive or. One or the other or both. These were for language. Our language, we have two different types of ors, and it depends on the context which or we are using. In mathematics, however, there is one or, and in math, we use the inclusive or. One or the other, or both. If you are to advance farther in mathematics, you may run into the exclusive or in a math class, and we give it a special symbol. We actually call it XOR for exclusive or one or the other, but not both. But again, that's a different class. On higher up, usually around discrete mathematics is where you see the exclusive or again. We always talk about inclusive or in mathematics. So, one or the other or both. This is called a disjunction. We saw before that an and inequality, an and compound inequality is called a conjunction. An or inequality is called a disjunction. And this is also known as a union, which is why you'll see that U between two sets. The U means or. So if we're talking about a union of two sets A and B, we have the possibility of values in A or values in B or values in both. This section here in the middle. In our example that we have here, x is less than -1. We'll throw some numbers on our number line. If x is less than -1 or greater than 3, we would graph the number line like this, x less than -1 or x greater than 3. And then we would simplify that number line, -infinity, -1, union 3, infinity. Just like we did with the intersections, the conjunctions, let's take a look at some simple, smaller sets and work through some examples. So we want to find the union of the sets 1, 2, 3, 4 and 2, 4, 5. Now, I do want to remind you that when we were doing conjunctions, when we had 1, 2, 3, and 4 intersected with 2, 4, and 5, we were looking at what do they have in common? What do they have that are the same? And we see that both sets have 2 and both sets have 4, So in the conjunction, this intersection equaled 2, 4. But for a union, we want what's in one set, or what's in the other set, or what's in both. We want everything. For a union, we would take everything in the first set, 1, 2, 3, 4, and then we look at the second set. We already have a 2, so I don't need to write it again. We already have a 4, so I don't need to write that again. But we don't have a 5, so I need to include the 5. Notice the difference between these two examples. The conjunction that we've done before, and then this disjunction, the union that we're doing now. Take a moment and see if you can find the union in number 13. Did you get all the numbers from 1 to 10 except for 9? 9 does not show up in either set. This would be our union. Something to note, if you had written this union in the order in which they showed up in our sets and put them together this way, this would be correct. The order inside the set itself does not matter when we're listing out elements like this. For our class, though, we don't do a lot of listing. We generally use inequalities. But this, again, just to practice what it is that we're doing. So what does it mean to have a union of two sets? Write it in your own words, but if I were writing it, I would say something along the lines of the union of two sets basically means take everything in both of the sets and put them in their own set. So everything in one set along with everything in the other set and throw them all together. Let's take a look now at some examples of disjunctions, compound inequalities with or. Unlike the and, we have to see the word or in these inequalities. That word or will show up every single time. And could have an and in it, or it could be that triple inequality, that three-part inequality that we saw a lot earlier. So let's take a look at this first one. 6x minus 4 is less than 2x, or negative 3x is less than or equal to negative 9. When we work through these types of problems, we're really working through two separate problems, and then at the end we'll put them together. So here, 6x minus 4 is less than 2x. We could subtract 6x from both sides, and we'll get negative 4 is less than negative 4x. And then we can divide by negative 4, but if we divide, we have to remember to change the direction of the inequality symbol, and we get negative 4 divided by negative 4 is 1, so we get 1 is greater than x, and we've simplified the left one. Now we work on the right one. Negative 3x is less than or equal to negative 9, so we need to divide both sides by negative 3, but we're dividing by a negative. We need to flip the inequality direction. Negative 3x divided by negative 3 will give me just x, and negative 9 divided by negative 3 will give me positive 3. So we have 1 is greater than x, or x is greater than 3. Now, this is just one example of how to solve it. To contrast, I could have the negative 3x less than or equal to negative 9. I'm going to show you why that flipping has to happen. If we just do adding and subtracting, we could add 3x to both sides, 3x minus 9, and then we could add 9 to both sides, and we get 9 is less than or equal to 3x. We didn't do any dividing or multiplying by a negative number, but notice my x is now on the other side of the inequality. If I divide by 3, which I should to get the x by itself, I'm dividing by a positive number, so I'm not switching that inequality direction. I get 3 is less than or equal to x, but that is the exact same as x is greater than or equal to 3. You don't have to divide by a negative. We could add and subtract to move things around and then do the division. We're still going to get the same answer. So all of the properties that I'm using here are still those same properties that we've talked about when we're working with inequalities. Now, if I take these two inequalities that we just found, the two parts to my answer, I have a number line we're looking at 1 and 3. 1 is greater than x. If 1 is greater than x, that means x is less than 1. X is to the left of 1. And less than, strictly less than, we've got a parentheses. And then x is greater than 3, to the right of 3. Greater than or equal to means we're going to have square brackets. And the instructions say to put the answers in set builder notation and interval notation. Set builder notation is pretty much take the inequalities that you just found for x and plop them in the curly brackets. So curly bracket x such that x is less than 1 or x is greater than or equal to 3. There's my set builder notation. Interval notation would be the simplification of the number line, negative infinity to 1, union, bracket, 3 to infinity. When we're looking at a union, we want to take everything that gets colored on the number line as our answer. So before, for the and inequalities, the conjunctions, the intersections, we were only looking at where the number line is colored by both, where they overlap, what they have in common, the intersection, where two roads meet. But here, for or, we just take everything that's colored. Pause the video, try number 16 on your own, see if you can come up with the same answer that I do. Remember, pause and then work it out on your own, come back and check, and if you make a mistake, correct it with a different color so that you can go back and review. Now for number 16, did you get x is less than 5 or x is greater than or equal to 8? You can see the number line, the set builder notation, and the interval notation for the solutions on the right. Let's take a look at number 17. Playing the same game, we need to isolate the x, so let's add 5 to both sides. I'm focusing on the left inequality first. 3x is less than or equal to 18. We need to get x by itself, so we can divide by 3. We're dividing by a positive number, so our inequality stays the same direction. X is less than or equal to 6. 18 divided by 3 is 6. And now that I've got the left one simplified to x by itself, we move to the right. 5x plus 2 is greater than or equal to negative 3. Subtract 2 from both sides. 5x is greater than negative 5, so we'll divide by 5 on both sides. Dividing by 5 is positive, so our inequality stays the same. X is greater than negative 1, and that line means we have or between them. We're just copying the or from up top. X is less than or equal to 6, or x is greater than negative 1. Now before I write the set builder notation or the interval notation, I want a graph. So let's put negative 1 and 6 in here. We have x is less than or equal to 6. So we'll take 6 and to the left. I'll use yellow to color this one out. And less than or equal to means we have a square bracket there. And then x is greater than negative 1. I'll start at negative 1. X is greater, which means x is to the right. Greater than means I have a parentheses there. Now, this is an or inequality. So for an or a union, we're going to take everything that is colored. Colored or shaded, however you want to say it. We take everything. So in this example, everything is colored. So here, our solution is all real numbers. Pick any number, any real number, and that real number will solve the first inequality, indicated by the yellow area, less than negative 1. Any number greater than 6 will solve the right inequality, and any number between negative 1 and 6 will solve both inequalities. Remember, one or the other, or both. That inclusive or gives us all real numbers for number 17.